Have you ever just, looked at an object and wondered how we actually measure the space it takes up? It's not just some abstract math class stuff. It's literally the language we use to describe our physical world. So let's dive in and see how a few simple shapes can help us understand the measurements of, well, pretty much everything.
I mean, really think about it for a second. That gift you need to wrap, the soda can sitting on your desk, even a book. They're all 3D objects, or solids, and they all have these two key properties that we can measure with some surprisingly simple and elegant formulas.
So here's what we're going to do in this explainer. We're going to start with what solids even are, then we'll break down 3 of the most fundamental shapes one by one. And don't worry, we'll finish with a super useful cheat sheet that puts it all together for you.
Okay, first things first. What in the world is a solid when we're talking geometry? Well, it's pretty straightforward. They're just 3-dimensional shapes. They have a length, a width, and a height. And to really measure them, we're going to focus on 2 big ideas: surface area and volume.
Let's start with surface area. Honestly, the easiest way to get this is to think about wrapping a present. The total amount of wrapping paper you'd need to cover every single surface of that box, with no overlaps, that's its surface area. It's basically the area of the object's entire outer skin.
Now, volume, that's a different story. Volume is all about the space inside the object. So if you took that same gift box and filled it up with water, the amount of water it could hold, that's its volume. So you got it? Surface area is the outside, volume is the inside.
Okay, let's kick things off with the simplest solid of them all, the good old cube. What makes the cube so perfect to start with is that everything about it is, well, perfect. Every single face is an identical square, and every single edge is the exact same length. And this is where it starts to click and feel really intuitive. Let's just build a formula from scratch. Imagine you have a little cardboard cube, and you unfold it flat. What do you get? You get 6 identical squares, right? If we call the length of a side A, then the area of one of those little squares is A times A, or A squared. Since you have 6 of them, the total surface area is just 6 times that. Simple.
And boom, there it is. The formula for the total surface area of any cube on the planet is 6a squared. It's clean, it makes perfect sense, and you didn't have to memorize it. You figured it out.
The volume is just as logical. You know how for most boxes, volume is length times width times height? Well, for a cube, the length, the width, and the height are all the same number, a. So it just becomes a times a, which is a cubed.
All right, let's build on what we know and talk about the cuboid. A cuboid is basically a cube that's been stretched out. Think of a shoebox, a textbook, a brick. The length, width, and height can all be different, which is why you see them everywhere.
So, just like the cube, we can figure this out by pretending to unfold it. But here's the twist. We don't have 6 identical faces anymore. What we have are 3 pairs of identical faces. The top and the bottom match, the front and the back match, and the left and right sides match. So all we have to do is find the area of each of those pairs, and then add them all up.
So when you add up the area of the top and bottom, the front and back, and the 2 sides, you get this: 2LB plus 2BH plus 2LH. And because mathematicians like to keep things tidy, you'll almost always see it written with the 2 factored out, which gives us this nice, clean final formula.
In the volume, oh, this one's the classic you definitely already know, just length times breadth times height. Super straightforward.
Now this is the aha moment. This slide shows you that a cube is really just a special kind of cuboid, one where the length, breadth, and height all happen to be the same. So watch this. If you take the big cuboid formula and plug in A for L, B, and H, you get 2 of A squared plus A squared plus A squared. That simplifies to 2 of 3A squared, which is 6A squared. It's the exact same formula for the cube we started with. See, the logic is all connected. It's perfect. All right, enough with the straight edges. Let's tackle a shape that has a curve, the cylinder. Think of a can of soup, a battery, a roll of paper towels. It's just 2 identical circles on the top and bottom, separated by a certain height. That curved side is what makes it interesting.
Now, how in the world do you measure that curved part? Well, this is the really cool trick. The top and bottom are easy. They're just 2 circles. The area of a circle is pi r squared, so for 2 of them, it's 2 pi r squared. But that curvy middle part? Imagine you take the label off a can of soup. What happens when you lay it flat? It's a perfect rectangle. The height of that rectangle is just the height of the can, h. And the width? It's the distance you went around the circle, which is the circumference, 2 pi r. So the area of that curved part is just 2 pi r h.
So let's put it all together. You add the area of the two circle ends, 2 pi r squared, to the area of that unrolled rectangle, 2 pi rh. That gives us the total. And just like before, we can factor it to get this clean final version, 2 pi r times r plus h.
And the volume. This follows a really beautiful simple logic. You just take the area of the base, that one circle on the bottom, pi r squared, and you basically just stack it up all the way to the height of the cylinder, h. So the volume is just the area of that base times the height, pi r squared h.
Okay, we have successfully deconstructed the cube, the cuboid, and the cylinder. We've seen why their formulas actually work instead of just taking them for granted. Now, let's pull it all together into one place for a nice, clean summary. This table right here, this is the kind of thing you'd see in a textbook, and it was the inspiration for this whole explainer. It's dense, right? But now, by breaking it down shape by shape, we've totally unlocked the logic hiding behind all those letters and numbers. And here it is, your ultimate takeaway. A simple, clean cheat sheet with the 3 solids we just mastered. But the great thing is, when you look at this now, you're not just seeing random formulas. You're seeing 6 squares. You're seeing 3 pairs of rectangles. You're seeing 2 circles and an unrolled soup can label. And this really gets to the whole point. These aren't just arbitrary rules that you have to cram into your brain. They are truly logical descriptions of the very shapes that make up our world. And that's exactly why this matters so much. When you understand the why behind a formula, when you can actually picture that label unrolling into a rectangle, it just sticks with you. It becomes a tool you can actually use, not just some random fact for a test.
So I'll leave you with this final thought. A skyscraper is really just a bunch of cuboids stacked together. A giant storage tank is just a huge cylinder. Now that you understand these basic building blocks, what complex objects out there in your world can you start to see and even measure in a completely new light?